So this is what we went over in class today, just in case any of you didn't make it or need a refresher. We talked about lessons 57, 59, 60, and 62. We're going to do chemical mixtures after Christmas when we come back, so I just kind of skipped those for now. Don't forget, you have a test next week, and it will cover all the kinds of problems. It's all explained on the homework sheet that I posted. It tells you exactly what problems to do and what kinds of problems will be on the test. So we're going to start with lesson 57, ideal gas laws. And we're going to look at the general ideal gas law, which says that P sub 1, V sub 1 over T sub 1 is equal to P sub 2, V sub 2 over T sub 2. What does that mean? Well, it means that if you have some quantity of an ideal gas, pressure, volume, and temperature relate to each other in this way. P stands for pressure. Pressure is measured in some of these units: newtons per square meter, atmospheres, millimeters of mercury, and pounds per cubic inch. Volume is V. Units for volume are things like liters, milliliters, and cubic centimeters. T stands for temperature, and we're going to be using kelvins for our temperature. This law describes, as I said, how pressure, volume, and temperature relate to each other. We're going to be talking about direct and indirect variation in a couple of lessons, but I'll basically just say that this law explains that pressure and volume are inversely proportional, which means that as pressure goes up, volume goes down. If you have some kind of gas and you put a lot of pressure on it, that means you're squeezing it and making it smaller in a sense. So the volume goes down as pressure increases. That means that pressure and volume are inversely proportional. And that's what this proportion here, this equation represents. And then pressure and temperature are directly proportional, meaning that as temperature goes up, pressure goes up. Volume and temperature are also directly proportional, meaning that if you raise the temperature, the volume also increases for an ideal gas. So we have 4 liters of an ideal gas at a temperature of 800 kelvins at a pressure of 100 newtons per square meter. If the volume were increased to 10 liters and the temperature reduced to 600 kelvins, what would the pressure be? Okay, so we are going to look at our ideal gas law. We saw it just a minute ago. This is how it's set up. And what we're going to do is we're just going to make some empty boxes and fill all the boxes in for pressure, volume, and temperature. We're going to talk about the pressure, volume, and temperature we start with, and the pressure, volume, and temperature we end up with after we make those changes. So the problem tells us that there are 4 liters of an ideal gas. That's volume. So we'll put that in the red box on the left side of the equation. It says the temperature of that gas is 800 kelvin, so we're going to put that where the temperature goes. It had a pressure of 100 newtons, so we're going to put that where the pressure goes. Now we're changing things. It says if the volume were increased to 10 liters. So now in the red box on the right side of the equation, we're going to put the volume that we change it to, which is 10. And the temperature is reduced to 600 Kelvin. So where we have temperature, T sub 2, we're going to put 600. And the question is, what would the pressure be? And so that's what we don't know. We don't know P sub 2. So all we have to do to find out what P sub 2 is just use the cross products. Since this is a proportion, you know that this product is equal to this product. So we would spell that out. 100 times 4 times 600 is equal to 800 times P sub 2 times 10. And so to find out what P sub 2 is, all we have to do is divide both sides by 800 times 10. And that's going to make all that stuff cancel out. And so P sub 2 is going to be, on top we'll have 400 times 600, which is going to be 24 with 4 zeros. And then on the bottom, we have 800 times 10, which is 8,000. So 3 of the zeros are going to cancel out, and we have 240 over 8, which is 30. And since this is pressure, we have to make sure we put the correct units on there. The pressure is in newtons per square meter, if you look at the problem. So newtons is N, and square meters is M squared. So that would be the pressure of the gas after we make those changes. Another one, the initial pressure of a quantity of ideal gas was 400 newtons per square meter, and the initial temperature was 1200 kelvins. The volume was held constant. What was the pressure if the temperature was decreased to 9000 kelvins? Now, in this problem, we need to notice that it says that the volume was held constant, which means that V1 and V2 are the same. We're not doing anything to the volume. And since we're not doing anything to it, it's just going to cancel out, so we might as well not even put it in the equation. So we're just going to set up the equation without the v's this time because volume was held constant. So we'll just fill in the other things. We have a pressure of 400 newtons to start with, so 400 is P1. And the temperature was 1200 kelvins, so that's T1. And it says that we are going to decrease the temperature to 900 kelvins, and we want to know what the pressure is going to be if we do that. So again, we're just going to cross multiply. 400 times 900 equals 1200 P sub 2. And so that's 36 with 4 zeros is equal to 1200 P sub 2. And if we divide both sides by 1200, then we are going to get P sub 2. 2 of these zeros are going to go away. And we're going to have 36 divided by 12, which is 3. So 300. And the units are newtons per square meter again. That is going to be the new pressure if we drop the temperature from 1200 down to 900. Okay, the temperature in this problem is being held constant, so we don't need temperature in our equation because it's just going to stay the same and it'll just cancel out. So we're just going to have this equation, P1V1 equals P2V2. So the original pressure is 7 atmospheres, and then we're going to put that in for P1, and the original volume was 42 liters. And so the volume was reduced to 10 liters, and the question is, what is the pressure going to be? So 10 P sub 2, divide both sides by 10, and we're going to have P sub 2 is equal to 7 times 42, which is going to be 294 over 10, which is going to be 29.4 atmospheres. This time the pressure was measured in atmospheres. So definitely make sure that you are getting the right units on whatever they're asking for. Okay, so that was lesson 57. But lesson 59 has a few things in it. One of them is experimental data. The data in the graph below came from an experiment involving bronze and copper. The shading around the points indicates that due to potential errors in measurement, the data may not be exact. The line represented by the data points has been estimated. Write the equation of the line which gives bronze as a function of copper. Note that the two scales are different. Okay, so a few things you need to know about this. This is basically just writing the equation of a line when you are given the graph of the line. But this is representing a particular experiment involving bronze and copper. You can see that the horizontal axis, which is usually the x-axis, represents the kilograms of copper in the experiment, and the y-axis represents the kilograms of bronze in the experiment. There's some relationship, some linear relationship between the kilograms of bronze and the kilograms of copper when you're doing this experiment. And if you've ever done an experiment, you know that things don't come out exactly ideally the way they might or should or we expect. And so you can see that the relationship, even though it's supposed to be linear, doesn't have a perfect line that goes through the points that were the data that was found in the experiment. And so what you have to do is just draw a line of best fit is what it's called. And so you just kind of draw a line that's close to all the points. It never gets too far away from any of the points. It kind of is an approximation of what that line should look like. And for now, when they give you these types of problems in the book, they will have already drawn the line. And so basically all you have to do is find 2 points on the line, find the slope, and find the y-intercept, just like you would do with any other problem where you're finding the equation of a line. And in this kind of problem, you're not going to call your variables x and y. You're going to call them whatever the problem is about. So this problem is about bronze and copper. Bronze is the y-axis, copper is the x-axis. So normally you would be writing y equals mx plus b for your equation of a line. But now you're going to be writing b for bronze, where you have a y, and you're going to be writing c for copper. Now I know that C is not the actual symbol for copper. It's actually the symbol for carbon, but I'm going to use C, even though the book uses the actual symbol Cu, because I don't think it's ever a good idea to use two letters for one variable. If you have a variable, you could have a subscript on it, like P sub 1, but you should never use two letters to represent one variable because it makes the equation ambiguous. It looks like two variables when there's only one. So for this math problem, okay, it's not a science problem in that sense, we're just going to use C to represent copper. So I could even off to the side here, I can say that B is the kilograms of bronze, and C is the kilograms of copper. C is not the correct symbol for that element, but we're using it as a variable in a math equation right now, okay? So let's look at how the line is drawn. We can pick 2 points on the line. The 2 points that seem to be most exact are this one and this one on that line. So be careful because, as it says, the scales are different. And what that means is your vertical axis here is counting by fives. Each square is worth 5, 5, 10, 15, 20, 25, 30. But your horizontal axis, the axis with copper, is 2.5 per square because 2 squares is 5, and then another 2 squares is 10, another 2 squares is 15. So just be careful because they don't always have to be the same. So if you look at this point over here, this is 5, 5. And this point is 15 for the horizontal coordinate and 40 for the vertical coordinate. So to figure out the slope of this line, remember it's going to be rise over run. And so if you use the slope formula where you subtract 40 minus 5 for your y, you're going to see that this line, the vertical line, is 35 units. And you can count that because you know that the vertical axis is broken up into units of 5 each square. So 5, 10, 15, 20, 25, 30, 35. The run is 4 squares. And since we know on the horizontal axis, every 2 squares is 5, that's going to be 10 total. The slope formula, remember, is going to be y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So you could do it that way, where you would look at your y coordinates, 40 minus 5, over your x coordinate, 15 minus 5, the difference in your x coordinates. And that still gives you 35 over 10, which is 7 over 2. So 7 over 2 is your slope, and that is equal to 3.5, which is what we're going to write it as, because usually in this kind of equation where you're in a science experiment kind of thing, you're going to use decimals. So we have our slope, m equals 3.5. And since I have that now, I'm going to erase all this so you can get it out of the way. And now we're going to fill that slope into the equation and find out what the y-intercept is. So b is equal to 3.5 c plus b. B is the y-intercept. To find that, I have to plug in a point. The easiest point to plug in will be the 5, 5 point. So b is 5, and c is also 5. So that is going to give us 5 equals 17.5 plus b. Subtract 17.5 on both sides, and you're going to have a negative 12.5 for b. And so now we know our b is negative 12.5, and we can write our equation. B is equal to 3.5 times C minus 12.5. That would be the equation of that line. And that's all you're doing is writing the equation of a line given the graph of the line. It's just that sometimes it won't be really clear which 2 points you should choose. Just pick 2 points that look like they're pretty close to whole numbers, and realize that sometimes there won't be any points that are exactly at the corner of a square. And so you may not get the exact answer as the back of the book, because depending on which points you pick, you might get a slightly different answer. But your answer should be very, very close to whatever is in the back of the book. So you just need to let your parent know, if they're grading it, that your answer just has to be close to the answer in the back for this kind of problem. All right. Simultaneous equations with fractions and decimals. So you're going to have these systems of linear equations just like you usually do with elimination and substitution to solve for x and y. But now you're going to have one equation with fractions and one equation with decimals. And you do not want to work with fractions and decimals in this kind of situation. You want to get rid of the fractions and decimals, and you do that by multiplying both sides of the equation by some number that will cancel all the denominators in the fractions, and that will move all the decimals to the far right of all the decimals. So, first of all, we're going to multiply this first equation, both sides of the equation, by 10, since the least common multiple of 2 and 5 is 10. So 10 over 1 is what we're multiplying this equation by. And therefore, when we multiply it out, 10 times x over 2, the 2 is going to cancel, and we end up with 5x. 10 times 3y over 5, again, the 10 and 5 will cancel, and we'll be left with a 2, so 6y. And then on the right side of the equation, the 10 cancels with the 5, and we're left with a 2. 2 times negative 2 is negative 4. So that's our first equation, no fractions anymore. All right, second equation, again, we have these decimals. There are 2 decimals, at the most 2 digits to the right of the decimal in any of those numbers. So we want to move all the decimals 2 spaces to the right. And to do that, we're going to have to multiply by 100, because 100 has 2 zeros, and it will move those decimals 2 places to the right. So when we multiply 10 by 0.06, decimal moves 2 places to the right, and we just end up with 6x. When we multiply 100 by 0.2, that decimal moves 2 to the right, and we end up with 20y. And then if we multiply 100 by 1.04, we end up with 104. So we have this system of equations, and we want to solve this. And I would say the best thing to do would be to solve it using elimination. Before I would even do that, I would divide that second equation by 2, because all the numbers in that equation are even, and it's just nice. So I'm going to divide that second equation by 2, and it'll be 3x minus 10y is equal to 52. So you don't have to do that, but it's just seemed like an easy thing to do. All right, so now we want to cancel something. I'm going to cancel the y's using elimination, because one of them is positive and one is negative. So I need to think about the least common multiple of 6 and 10. The lowest number that 6 and a 10 both go into is 30. So if I multiply the top equation by 5 and the bottom equation by 3, I will get my y coefficients to be the same but opposite. And that's what I want, so that they will cancel out. So 5 times 5x is 25x. 5 times 6 is 30y. And 5 times negative 4 is negative 20. Second equation, 3 times 3x is 9x. 3 times 10y is negative 30y. And then 3 times 52 is going to be 156. And now if I add the two equations together, the y's will cancel, and I'll have 34x is equal to 136. And so if I divide both sides by 34, I get 4 for x. And now to find out what y is, I can just take that x and plug it back into any one of these equations I started with. I think I'll just plug it in right there at the 5x plus 6y equals negative 4. So 5 times 4 plus 6y equals negative 4. So if I subtract 20 on both sides, I'm going to have 6y equals negative 24. So y is equal to negative 4. And so the point where these two lines cross, the solution to this system of equations, is 4, negative 4. All right, now we're going to change rectangular coordinates to polar coordinates. Be sure that you know how to change polar coordinates to rectangular coordinates. You've been doing that for a couple of weeks now. I hope that you have got that nailed down. Now we're going to do it the other way. We're going to convert from rectangular coordinates to polar coordinates. So we want to convert negative 5, negative 3 to polar coordinates. So negative 5 is 5 to the left, -3, that's 3 down. That put us in the third quadrant. And there's the point. We're going to draw a radius from the origin to the point. That's going to be our hypotenuse of that right triangle. And our angle is going to be the angle between that hypotenuse and the x-axis. So the first thing I'm going to do in this problem is find theta. But theta is not going to be the angle in my answer. Remember, we are in the third quadrant. Remember the quadrants. Go like this. We have quadrant 1 here, quadrant 2 here, quadrant 3 here, and quadrant 4 here. And we start out at 0 degrees, 90 degrees up here, 180 here, 270 here. So if I am in the third quadrant, this angle from 0 is going to be somewhere between 180 and 270. To find theta, we're going to need to use tangent because we have the opposite side to theta, which is 3, and we have the adjacent side to theta, which is 5. That is tangent. So tangent of theta is equal to opposite over adjacent. And since we don't know the angle here, we're going to be using inverse tangent to find out what theta is. We don't want to take the tangent of 3/5. 3/5 is not an angle. You don't take tangent, sine, cosine of a proportion. You take tangent, sine, cosine of an angle. We don't know the angle, so we can't use tangent. We have to use inverse tangent. So angle is missing. I know the ratio, so inverse tangent of 3/5 is going to give me the angle. So to punch that into my calculator, I am going to hit the following buttons. 3 divided by 5 equals second, or inverse, whatever your calculator has, tangent, and that is going to be theta. You are going to get about 31 degrees for theta. And so to find h, I am going to use the Pythagorean theorem because this is a right triangle. I know the legs. I don't know the hypotenuse. So the best thing to do is to use the Pythagorean theorem. Your book uses sine and cosine with this angle 31, but since 31 is not exact, it's only an approximation, the most exact answer will be using the Pythagorean theorem. And according to the Pythagorean theorem, 3 squared plus 5 squared is going to be h squared. And so 9 plus 25 is going to be h squared. 34 is equal to h squared. And if I take the square root on both sides, I'm going to get square root of 34 equals h. Now, if you punch that into your calculator, you get about 5.83 for h. On a test, I would tell you what I want. I would say approximate the answer to 2 decimal places if I wanted you to write it this way. If I wanted you to give me the exact answer, you would need to write it that way, square root of 34. That is the only way to write the exact answer. So if I say give me the exact answer, I mean square root sine 34. There is no other way to write that exactly. 5.83 is an approximation. You just chopped off a bunch of other numbers that were in the answer. It's actually an irrational number, so you could never write it exactly because those decimals would go on forever. So this is the exact answer, square root of 34. This is the approximation that has been written to 2 decimal places. So make sure you know the difference. All right, so our answer, I'm going to use the approximation because I think that's what your book does on this problem. Your answer is going to have that 5.83 outside this little bracket, and inside the bracket, you're going to have to put the angle, which, as I said, is going to be 180 plus theta. So 180 plus 31 is going to be about 211 degrees. So this is how your answer should look. Okay, direct and inverse variation. As I was mentioning in that problem with the ideal gas laws, we talked about when you have a situation where 2 quantities are related to each other, they depend on each other in some way. And as one changes, the other changes. Direct variation is when we have two quantities that go up together and they go down together. Inverse variation is when, as one quantity goes up, the other goes down. All right, so we can write equations that will help us understand the relationship between quantities that vary directly or inversely. So if y varies directly as x, and another way to say that is y is directly proportional to x, then we can write the mathematical model y equals kx. This is how you would set up an equation that expresses that situation mathematically. That's called a mathematical model. K is some constant that relates the two things, whatever they happen to be, and it just depends on what the situation is. So that would be how you would set up a direct proportion. And then inverse proportion, y varies inversely as x. In other words, y is inversely proportional to x, and it could say indirectly. Inversely and indirectly are synonyms. If that is the case, then y is equal to k over x. K, that number k that we're going to have to find out, is called the constant of proportionality. And you'll see how that works in an example in just a second. But first, let's set up some models for this kind of proportionality. So the first problem says the amount of medicine A prescribed varies directly as the weight of the patient, which makes sense. The more you weigh, the higher your dosage is going to be. So those two quantities go up together or down together. If you weigh less, you have a lower dosage. So the amount of medicine A varies directly as the weight of the patient. And the way we can model that mathematically is to write the equation A is equal to K times W. That's a direct proportion. And K, like I said, is some constant, and it would depend on what kind of medicine it is, and what medical science has figured out is the right dosage for different weights. The frequency, F, in a vibrating string is inversely proportional to the length of the string. So if you're dealing with an instrument that has very long strings, when that string vibrates, the frequency is much lower. So the higher the length, the lower the frequency. So these are inversely proportional, and I would say that F is equal to K over L. When you have an inverse proportion, the other letter goes in the denominator. All right, the last one says the variable y varies directly as the square of x and inversely as the square root of z. So this situation has two different kinds of proportion, two different kinds of variation. So y varies directly as the square of x, so kx squared, but inversely as the square root of z. So the square root of z would go on the bottom. So this is how we set up these kinds of variation problems. And now we're going to do some examples. All right, the number of boys in every classroom of a school varies directly as the number of girls. So direct proportion, number of boys is equal to K times the number of girls. In one room, there are 8 boys and 2 girls. All right, so this information now is going to help us figure out what K is. Because if we know there were 8 boys when there were 2 girls, that's going to tell me that K has to be 4 because we divide both sides by 2, which is 4, and that is K. So now we know what K is. And so our equation that shows you the relationship between the boys and the girls is that boys equals 4 times the number of girls. So when I'm asked this final question, now that I know K, I can figure this out. So set up the second situation using 4 for K, which is what I did. If there are 5 girls in another room, how many boys are in this room? So all I have to do now is put in 5 for girls. So the number of boys is equal to 4 times the number of girls. And in this last sentence, it's telling me there are 5 girls in this other room. So the number of boys is going to be 20. So 20 boys. So in these kinds of problems, the first thing you do is find out what that constant is, that constant of proportionality. You use the information they give you to find K. Once you find K, they're going to give you some more information, and you will be able to solve for one of the variables, one of the unknowns, using K. All right, so here's another example. The number of revolutions per minute varies inversely as the number of teeth in the gear. If 40 teeth result in 100 RPMs, what would be the RPMs if the gear had 30 teeth? All right, here's another situation where I do not want you to use multiple letters to represent one variable. So do not use RPM to represent revolutions per minute. Those are the units that you will have for your answer, but you would not want to use 3 letters to represent one quantity. So just to remind myself what my letters mean, I'm going to say that R is equal to revolutions per minute, and I'm going to let T be the number of teeth. So now I'm going to set up my equation. It says that the revolutions per minute, so that's R, varies inversely as the number of teeth. So K over T. So this is the setup. This is the mathematical model that represents this situation. And now I'm going to take the information they give me to find out what K is. They are telling me that if there are 40 teeth, the result is 100 revolutions per minute. So plugging that in, 100 revolutions per minute is K over the teeth, 40 teeth. And so if I multiply both sides by 40, I'm going to get that K is equal to 4,000. This is the constant of proportionality that explains the relationship between the number of teeth and the RPMs. So now we want to find out what would be the RPMs if the gear had 30 teeth. So we're just going to use our original equation, but now we know K is 4,000. So RPMs we're looking for, we don't know. What would be the RPMs if T was 30 now? So K is 4,000. We already know that. And T this time is 30. So that is going to be 400 divided by 3, which is going to be 133 and 1/3 RPMs. All right, the number of clowns was directly proportional to the number of performers. So that's pretty easy. C for clowns, P for performers. So the number of clowns is directly proportional to the number of performers. So that's K times P. If there were 40 clowns, there were 20,000 performers. To solve for K, we have to divide both sides by 20,000. So K is equal to 40 over 20,000. 0.002 is K. So now that I know what K is, I can use this equation with K plugged in to find out the answer to the next question, which is how many clowns would there be if there were 1,200 performers? So clowns is equal to KP. K we know now is 0.002, and we're talking about 12,000 performers now. And if we multiply that out, we are going to get 24 clowns, which is much better than 40, though not a whole lot better, but it's better, a little better. I don't know how you feel about clowns, but I think the fewer clowns, the better. All right, so that is direct and inverse proportionality. And now we're going to look at complex roots of quadratic equations in lesson 62. This is just completing the square. There's no difference in what you do for these problems, but the answers you get are slightly different because you're going to end up needing to use Euler's notation to write your answer, and you will see why in just a second. So we want to solve this quadratic equation, and we have to use completing the square to do that. So 3x squared minus x plus 5 equals 0. You want to get all your terms in order from the highest power of x down to the constant in order, and you want everything on one side so that it equals 0. Now you need to notice that the leading term has a coefficient of 3, which is not 1. It needs to be 1. So we are going to divide everything by 3. And we will end up with x squared minus 1/3 x plus 5/3 is equal to 0. And so now we can do our little thing where we leave a blank after the x term, and we move the constant to the right and leave a blank over there as well, because we're going to add something to both sides of the equation, and that something is going to be half the x coefficient squared. The x coefficient is 1/3. 1/2 of 1/3 is 1/6. And when we square that, we're going to get 1 over 36. And now we can write the left side of the equation as a perfect square binomial. It's going to be x, then we're going to put a minus sign because there's a minus sign right there. And then the number that goes next is half the x coefficient. So half of 1/3 is 1/6. So that is the whole left side of my equation. There's nothing else over there. It is a perfect square binomial. And then on the right side, I'm going to need to add these two fractions. And when you add fractions, you have to find a common denominator. And so -5/3 is going to be -60/36. And then you're going to add 1/36. And that's going to be -59/36. And now to solve for x, you will take the square root on both sides. Don't forget to put plus or minus on the right side. And so the square root will cancel the square, and you'll end up at x minus 1/6. And on the right, you will have plus or minus the square root of -59 over the square root of 36. And that is going to be plus or minus the square root of 59i over 6. Now you want to get x by itself, and unfortunately I'm out of space, so I'm going to do it up here. I'm going to rewrite it. X minus 1/6 equals plus or minus the square root of 59i over 6. And now to get x by itself, I'm going to add 1/6 to both sides. 1/6 plus or minus the square root of 59 over 6i. This is how you want to write your answer. You want the real number first, 1/6, and you want the imaginary part second. Completely separate from the real part. Real number here, imaginary number here. Okay, one more. Again, we're going to get everything in order. 5x squared comes first, then the x term. Then I'm going to move the 3 to the left. I'm going to move 3 to the left. And actually, if you're getting pretty handy at these problems, since you know you're going to put the constant back on the right side anyway, you could go ahead and leave it over there if you want to. All right, the first thing we have to do is divide everything by 5. Gotta have a 1 for your leading coefficient. That's going to give us x squared minus 2/5 x plus 3/5 equals 0. And now we're going to move our constant to the right side of the equation and leave a blank here. So -3/5 plus blank. Again, the thing that we're going to add is half the x coefficient squared. And I'm going to notice that these 2's cancel, and 1/5 squared is 1/25. So I'm adding 1/25 to both sides of the equation. And now I'm going to write the left side of the equation as a perfect square binomial, x minus half the x coefficient. And remember, half of 2/5 is just 1/5 because the 2's cancel. So 1/5, x minus 1/5 quantity squared. And over here, I'm going to have -15/25 plus 1/25. And that's going to be -14/25. So x minus 1/5 quantity squared is equal to -14/25. I'm going to take the square root on both sides, putting plus or minus over here. And so my square is going to cancel out. And I have x minus 1/5 is equal to plus or minus the square root of -14 over the square root of 25. And just like I did last time, I ran out of space. So I'm going up top. X minus 1/5 is equal to plus or minus the square root of 14 over 5i. Add 1/5 to both sides, and you get x by itself. And this is your answer, with the real part first and the imaginary part second, completely separate, using Euler's notation. And that is how it's done. So that's complex roots of quadratic equations.